Let us know about some examples of conservation of angular momentum. Some examples of conservation of angular momentum. The principle of conservation of angular momentum is used by acrobats in a circus, skaters, drivers in a swimming, and ballet dancers. In each example, they can change their angular speed by changing the moment of inertia, which depends upon the distribution of mass about the axis of rotation. Here, red line is the axis of rotation. When a swimmer or driver stretches the body, the distribution of mass about the axis of rotation increases. Hence, the moment of inertia increases and the angular speed decreases. Hence, the frequency of revolution of a body also decreases. Whereas, when a swimmer or driver folds the body, the distribution of mass about the axis of rotation decreases. Hence, the moment of inertia decreases and the angular speed increases. As the angular speed increases, the frequency or the revolution also increases. In all these applications, the product of moment of inertia and the angular speed, that is the angular momentum, is constant once the player acquires a certain speed. Consider the example of ballet dancers. During the ice ballet, the dancers have to undertake rounds of smaller and larger radii. The dancers come together while taking the rounds of smaller radius, that is near the center. In this case, the moment of inertia of their system becomes minimum and the frequency increases to make it thrilling. In this case, the dancers have to fold their hands so that the distribution of mass particle about the axis of rotation decreases. Hence, the moment of inertia of the system decreases. Thus, the angular speed increases, which increases the number of turns. Whereas, when the dancers undertake outer rounds, they outstretch their legs or arms so that the distribution of mass about the axis of rotation increases. This increases the moment of inertia of the system. Hence, the angular speed as well as the linear speed of the dancer decreases. Hence, the frequency of revolution also decreases, which prevents them from sleeping. In each position, they have a angular momentum so that the total angular momentum of the system remains constant. Angular momentum with stretching hands as shown in figure 1 is given by L1 is equal to I1 omega 1, where L1 is an angular momentum with a stretching hand, I1 is a moment of inertia of the system, and omega is a angular speed. Angular momentum with a folding hands as shown in figure B is equal to L2 is equal to I2 omega 2. Using the principle of conservation of angular momentum, L1 is equal to L2 because the total momentum of the system remains constant. Hence, we can write down I1 omega 1 is equal to I2 omega 2. This is a formula for the principle of conservation of angular momentum. Consider the another example of conservation of angular momentum. Diving in a swimming pool. While on the diving board, the drivers stretch their body so as to increase the moment of inertia. Here, in this position, the distribution of mass particle about the axis of rotation increases, hence the moment of inertia also increases. Immediately after leaving the board, they fold their body immediately so that the distribution of mass particle about the axis of rotation decreases, which reduces the moment of inertia considerably. As a result, the frequency increases as the angular speed also increases, and they can complete more rounds in air to make the show attractive. Again, while entering into the water, they stretch their body into the streamline so that their moment of inertia increases, which allows them a smooth entry into the water. In this case, the total angular momentum of the system is conserved, and hence we can write the equation as I1 omega 1 is equal to I2 omega 2, where I is a moment of inertia of the system and omega is a angular speed.